Okay, hi Year 12. This is the start of our last topic in the Year 12 Advanced course, and it is called Continuous Probability Distributions. Now, I'm not going to follow chapter 10 in the Cambridge textbook. I'm going to follow an old Margaret Grove Maths in Focus book, and it's chapter 14. So I've got those chapters sitting in the OneNote for you. I think it'll be a little bit easier and a little bit, just a little bit better to follow that textbook. So we're looking at PDFs, probability density functions. Now, we've looked at these before. We've looked at discrete probability density functions, and we're going to now look at continuous ones. And before we have a look at those, I want you to think back to Year 8 and have a look at what is the difference between discrete and continuous data. And you can have a little read through there. I won't read it out to you. You can pause the video and have a look. Okay, but the main thing I'm going to look at is this last paragraph that says discrete data is the type of data that has clear spaces between it. They're kind of like counting numbers, okay, like zeros and ones and twos, etc. Continuous data is data that falls in a constant sequence, and that's generally a measurement. So we might have 0.01, 0.001, and an infinite number of numbers between each of our counting numbers, and we call that continuous data, and that's the data that we're going to be having a look at in this topic, and we generally look at that data in terms of a graph. So the PDF, or the probability density function, is a function of a continuous random variable whose integral gives the probability of x less than or equal to x. Okay, that'll make more sense soon, and the sum of all probabilities are 1. So in our discrete PDFs that we looked at in Year 11, we had a tabulated form of probabilities, and the sum of our probabilities was equal to 1. That's still going to be the case, but we're going to have a function of f of x that describes our continuous data, and we're going to have that the area underneath that function is equal to 1. Still, all the sum of all the probabilities are shown underneath that graph, and then we're just going to pick off different parts along the x-axis and figure out what that area is, and that will help us answer that question. Let's have a look at the first one here. An example says a function is given by f of x is equal to 3x squared on 26 for x between 1 and 3, and all other parts of that is equal to 0. So it's a parabola, but what it basically looks like is a very flat parabola like this between 1 and 3. So what I actually want to do is I don't want to have all those parts in there because some of it is 0. So between 1 and 3, our graph will look like that. Less than 1, it's 0. Greater than 3, it's 0. So our function that we're looking at is this. Okay, and it's telling us that, well, we don't know actually that it's a probability density function. We're going to find that out. So if this area is 1, so if the area is equal to 1, then it is a PDF. And that's basically what we're going to use to describe our PDFs. So let's work that out. So to find the area under a curve, remember we integrate. So we're going to integrate this function between 1 and 3. I'm not going to explain how to do that. We've done lots of integrating, add to the index, divide by the index, sub in the 3, take away what we get when we sub in the 1. If we do that, we end up with 1. So you can pause the video and check that that's the case. So because it does equal 1 to 1 in that domain of values, then we say that yes, this is a continuous probability distribution. If it wasn't equal to 1, then it wouldn't be. And that's a great way to test it. The next question tells us it is a probability density function. So a function is given by f of x is equal to ax squared, and it's defined in the domain 0 to 5. We want to find a for which this is a PDF. So if it is a PDF, then we know that the area under this curve, ax squared, between our values of 0 and 5 is going to be equal to 1. So if I integrate ax squared between 5 and 0, it's going to be 1. So I can use that information to figure out what a is going to be. Okay, so if we add 1 to the index, divide by the index, we get ax cubed on 3. Pop 5 in, take away what we get when we pop 0 in, and I end up with 125a over 3. That is equal to 1. And then I get a is 3 over 125. So that's how we deal with a question like that one. So you're going to go through the exercises and have a look at 1401. Fairly simple, just remembering if it's a PDF, the area under the curve in that given domain is 1. If we want to find out if it's 1, let's work out the area and see what we get.